Okay, so none of us here works really in this area, and the question was initially raised by Dror Feitelson, and his motivation comes from Dror is working in the theory of systems, large systems in computer science, and so to the little extent that I will be talking about the potential applications of this is what I will have in mind. But it seems to me that some of the questions and some of the techniques go beyond this kind of application. Okay, so the setup is quite simple. We have n users, and they're sharing m resources. Okay, and I can assume, and I will, that costs nothing. I mean, in terms of limiting the applicability, there is a unit resource, a unit. 1 unit of supply of each resource. Then there is another ingredient of the model, which is entitlement, which is a little bit less obvious to understand, so I will explain it a bit later on. For the moment, these are just positive numbers. One, so associated with each user is one positive number called displayer's entitlement, EI, it's positive, and the sum of the EIs is 1. So bear with me in very soon you'll understand precisely what these are. And the users want to make use of the resources, and they apply the requests. User I requests Rij of resource j, and these are non-negative numbers. This is one of the critical aspects of this model. We're in a situation where you cannot exchange. So if you're thinking about really the computer system application, it's not possible for you to, for example, have more CPU and less bandwidth, and you would still be able to do what you want. So these numbers are fixed. So users are unwilling, or perhaps if you're thinking about other situations, perhaps there are external rules that rule out these possibilities. These numbers are carved in stone. You cannot change them. So what we're allowed to do is find a factor that we will multiply the requests of each user by. So what we have to do is select positive numbers, xi, for the ith player, and provide the ith player with this much, xi times his request of capacity j for every j. Or perhaps in a more picturesque way, I want to have fruit salad. In my fruit salad, I want to have 20% of bananas, 10% of apples, and so on. The proportion, how my fruit salad is going to be composed, that's a given. You cannot touch it. How much of it? Well, I'd like to have as much as possible, and let's say you're running the show. You'll decide how much you're going to give me. So just to wrap up, this is a technical part of the presentation. So we're given these numbers Rij, we're given the numbers EI, and our job at the moment, we still haven't specified it, is to seek some positive numbers xi, where the main aspect is going to be, there are two things, feasibility and fairness. Okay, feasibility is quite obvious, and the non-trivial parts coming in explaining what fairness means. But feasibility is obvious to you. We have 1 unit of supply from each resource, and of course we cannot give more than we have. So in other words, if you take any resource, then what you have given away from this resource cannot exceed 1. That's quite obvious. This is what we've given from resource j to player I. We're summing over all i's, and that cannot exceed 1. And if you're used to linear programming and this kind of thing, and I think many of you are, then what we're looking for looks quite familiar if you saw linear programming, but wait, this is not a linear programming problem. You'll see soon. What we're looking for is a positive vector x such that x times r is less than 1. Big R is the matrix whose ij entry is Rij, how much player I is requesting from resource j. Okay, now I have to talk about entitlement. It's part of the problem definition. and I have to explain what this means or what this could mean. And this can be interpreted in more than, or could mean different things in different setups. If we're really talking about a big computer system, then perhaps it's a system that was built up by several users, and each one contributed that much money to the creation of the system, and therefore this tells you how, this determines this user's entitlement. Perhaps it's, all these users are part of one bigger thing. Perhaps there are different departments in one bigger operation, and management decides to give priorities to different activities. And another possibility is that actually they're not big N users, but actually they're big M, which is a much bigger number of users. And we are really respecting each player or each user in the same way. So you could think of what will correspond later on to entitlements of 1 over M. The role of N in this description is that there are big N types of users, and the EI just tell you the proportion of users from each type. That's the meaning of entitlement. Okay, so far I think everything is quite simple and clear. If you have any experience with optimization problems, everything should look very familiar and easy. This is the most subtle part, and I have to admit that it took me some time to get used to this definition, so let me elaborate on this. When do we define, how do you define fairness? So the key ingredient in understanding fairness is the notion of bottleneck. That's still very simple. We say that a certain resource is a bottleneck resource in a situation that, so let's just make sure. E, the vector of entitlements, R, the matrix of requests, that's fixed. Now we've already also chosen a positive vector X. Not yet. That will come. That will come. And you say that the jth resource is bottleneck if it's used up. In other words, if the jth coordinate of this vector, X times R, is 1. That's called the bottleneck. But make sure that you follow this point, that this definition of bottleneck depends on the choice of X. And now we come to fairness. And this, I think, conceptually is the most subtle part of this talk. So when do we want to consider this allocation? So X determines the resource allocation. When do we want to consider it fair? What we want is to make sure that we somehow satisfy each user, or that no reason, as the title of the talk says, that no user has any grounds for complaining about the fairness of. So one possibility, we're looking at user I. Perhaps xi is 1. In other words, you got what you asked, and there is no reason to complain. The other possibility is the most subtle part. Perhaps you have not received everything that you've requested, so xi is less than 1. However, there is a bottleneck resource on which what you're getting is at least your entitlement. In this case, this is when we define X to be fair. So, in other words, and as I said, that's the most subtle part, so let me elaborate on this. For each user, either the user is receiving the full his full request, or there is a resource on which this user is receiving this user's entitlement. But moreover, this is the bottleneck resource. So if I wanted to increase the share of this user, then I have to harm other users, because there is a bottleneck resource on which this happens. So in other words, this is what we call, there are no reason for justified complaints. So let's talk about this. Let me just say, the two main things that I'm presenting here is this definition that I just presented, and a theorem that says that such a solution always exists. And I will say a few words about how this is proved, because there is something quite interesting, and at least something that I haven't seen elsewhere, so it's perhaps interesting to explain. Okay. So if you're like myself and you've done a lot of linear programming, this looks very much like a linear program, and it's very natural to try and use the machinery in linear optimization to somehow solve the problem this way. But this is not. So the point is this. If the set J of bottleneck resources is fixed, then finding the X is a linear program. But there are 2 to the m such possible subsets. In particular, this gives you an exponential in m algorithm to do this. But without knowledge of this, it's not a linear program. In particular, as we'll see, I will show you some examples, and I will give you more indications on why this is not. I'm not saying perhaps there is a way to do some very clever exercise and apply LP here. But certainly what I'm saying, at least not in the obvious way. I wasn't able to make an obvious connection, and it seems quite different. I'll show you later. So here, let's take a very simple example just to illustrate. Let's say that this is the request matrix. So everyone is requesting 1, except that user I is requesting 0 of resource I, and otherwise they're requesting 1. Well, here are 2, and all entitlements are a quarter. So here is one possibility. X is a quarter, 3/8, 3/8. Okay? It's very easy to check that this is a feasible and fair solution where the bottleneck resources are 1 or 2. But of course, you see the symmetry here, so you wouldn't be surprised that there is also this solution, 3/8. This is why I chose a simple example that's easy to see on the fly. So 3/8, 3/8, a quarter, and a quarter is also feasible and fair. And here, the bottleneck resources are 3 and 4. So let's average these 2 solutions. You get 5/8, 5/8, and so on. This is a feasible solution, but it's not fair. So this is really, in some way, not a very good example, because as everyone will see immediately, the right thing to do here is give everyone a third. And then you're completely using all the resources. It's, of course, feasible and fair and so on. But this is just to illustrate that one basic property that you get in solving linear programs doesn't hold here. And so this is a different, it's a different. 5/16. Thank you. Sorry. Yes.
So for that solution, you wrote up, why is this fair?
Why is this fair? Because, well,
it doesn't seem to exhaust any of the resources.
no, it exhausts, let's say the first one, it exhausts not 1 and 2. Twice 3/8 plus a quarter is 1. So here is the theorem. The theorem is that such a solution always exists. So give me a matrix of Rij, which are between 0 and 1. Give me entitlements, which are positive and add to 1. Then there exists a vector x that's positive, such that xr is less than or equal to 1, so that for every I, there is an index there is a bottleneck index for which xi times Rij is how much user I is receiving from resource j is at least this user's entitlement, and where j is defined. That's the main theorem. Okay, and I will. No. Oh, that's the definition. That's the set j. Okay. So that's a theorem, and I will tell you a little bit about how this is proved. Okay, so of course, one thing that you learn when you do optimization and so on is that the right way of looking at questions like this is geometric. So let's look at these things geometrically. So the constraints that x is positive and xr is less than or equal to 1, as usual, that defines a convex polytope. And this polytope is sitting in the positive orthant of the n-dimensional space. This is the positive part. And each constraint is a hyperplane, which is a facet of this polytope P. Well, actually, as I initially presented the problem, perhaps there are resources that are redundant. I mean, you solve everything, then automatically you solve them, then you do a pre-processing and you throw those away. So really doesn't matter much. So this is the setup. From this perspective, from this geometric perspective, what does it mean that the solution is feasible? It just means that X is this polytope P. Fairness means that X has to sit on the upper boundary. So I'm using this notation for boundary just to make sure that I'm not talking about the hyperplanes xi equals 0. So this just refers to the upper part of the boundary of this polytope. So in order to be fair, you have to be on the boundary. There is more conditions there. It's more subtle, but it's necessary. So we're looking for points on the upper boundary of P. And I don't go into the precise details here, but the set J, as we said, what's bottleneck depends on X. How do you see it geometrically? It's precisely determined by the set of facets on which you reside. So it's a polytope. Vertices of this polytope are where certain facets meet, and your bottleneck resources are precisely corresponding to, so you're at a vertex, let's say, then, or at another higher dimensional face, certain facets meet there, these are exactly the bottleneck resources. So this is how the geometry and the definition as an optimization problem complement each other. So why is it difficult? If you start thinking about these things, it's really, perhaps, let me take a minute. And the first thing that you normally do in a situation, just to get a feeling for this, is you do this with two users. You do this in the plane. And then the problem is really easy, because the polytope P is just a polygon. And you simply scan the vertices in order. And one of them will solve what you want, and that's it. You're happy. It's very simple. So in n equals 2, this theorem is really easy. What complicates matters is that in higher dimensional space, convex polytopes are quite complicated combinatorial objects. There is the whole structure of the face lattice of a polytope, and that's a complicated mathematical object, and we don't have good algorithmic methods to deal with it. It can have exponentially many vertices. It's a tough thing to deal with. And so, perhaps a little paradoxically, the idea came up that perhaps in order, if this is where our trouble is coming from, this complexity is coming from the rich combinatorial structure of this polytope, perhaps we avoid the combinatorics altogether and try something continuous. So what about this domain? It's a closed down domain in n space. Reduce the coordinates you're staying in, because that's a matrix R the matrix R is a non-negative matrix. And we're trying to replace this domain P by another domain Q that sits in the first quadrant of Rn that in many respects is very similar to P. It's closed down, it's convex, except I want to smoothen out this upper envelope with the hope that that will simplify things for me. So what I want to consider instead of this polytope P that I had before is a domain Q that's convex, closed down, and has a smooth upper boundary. Okay, sounds perhaps a little strange, but as you will see, I mean, this immediately raises more questions than answers. But let's see, the situation is, you'll see, is quite good, but it takes a little thinking how to get there. But so let me first raise the questions that come up. How do you even describe this domain Q? How do you test feasibility? What happens to fairness? Previously we said that fairness is determined by the set of, or in order to, even bottlenecks are determined by the set of facets on which your X lies. What happens to all these things? So things are not so bad. And we start with an easy observation. By the way, here this should be a max. This means should be a max. We can express this P as X is positive. The vector X is positive. And in addition, there's this function phi that's less than or equal to 1, where phi is the max of the R. This is just another way of saying it. It's really, I'm not saying here anything useful, just the fact that it is possible to express the domain P in terms like this. So what I want to do is to replace this function phi by another function and see if, so I want to replace p by some f and consider a domain Q that's defined like this. X is positive, X is in Rn, and f of x is less than or equal to 1. What about this f? I just want to more or less mimic the same things that I had in the original problem. It has to be concave, it has to be positive in the vicinity of the origin of Rn in the first quadrant. It has to be monotone decreasing in each variable and sufficiently smooth. But don't worry about this. This is really what I'm saying here. I want P to look exactly like Q, except to have a smooth upper boundary. This is, I mean, so we at the moment only have difficulties with it, and the question is, can we really get this off the ground? Well, we said the first question is, can we test feasibility? Yes, of course. All you have to do is check that x is positive and f of x is less than or equal to 1. What about the bottlenecks? That looks like the most difficult part. But actually, this is exactly where we're gaining. What seemed initially perhaps, how would you go about this? This is precisely where we're gaining. Why? You see, Q now is something smooth. And you want to be, it's a smooth domain that's defined by x positive and f of x less than or equal to 1. How do you define geometrically a convex smooth domain? You take all the tangent planes, there are uncountably many of them, and you say I have to be below that hyperplane. So rather than the finite list of inequalities there, I mean, it seems, again, at the moment it doesn't seem too promising. It seems like we're really going, with our heads against the wall, but you'll see, don't worry. We're replacing the finite list of inequalities that we had before by an infinitely, uncountably many inequalities, one per each hyperplane. But this is precisely where we're going to gain. So again, we want to consider only points on the upper boundary of Q. Feasibility is automatically there. And now we understand that we have to consider Q as being defined by the intersection of all half spaces, one per each tangent plane. Okay, so that's how what a typical tangent hyperplane looks like, just like any hyperplane. And this hyperplane, so to be tangent, this means that this vector A here is a normal to Q at the point that it touches this domain Q. And every point in Z, every point Z in Q is determined by satisfying all this collection, uncountably many inequalities of this form. Every hyperplane, you have to, that's a tangent, you have to lie under this hyperplane. So now think about this. You have a smooth domain like this. You have a point on the boundary. But now there is precisely, you can precisely characterize this point. Why? It has to satisfy all these inequalities. But there is one inequality that it satisfies with equality. The inequality that corresponds to the tangent hyperplane at this point. Okay? So this precisely captures the property that you want. What this means that in the smooth situation, we are really in dealing with a problem like this. Rather than the finite list of inequalities that we had, you have uncountably many restrictions, but every resource, at a boundary point, every resource is a bottleneck resource. So now the thing that made the problem difficult before was that the set J was hard to get our hands on. And now, although it's uncountable, we have it in everything, every resource is a bottleneck resource. And, okay, so I'm cheating here a little bit, but let's. Yes. Right, exactly. Okay, so now we've completely eliminated the trouble with the combinatorial complexity of the problem. And fairness, that's another thing. Fairness used to be an inequality. It's now becoming an equality, okay? So even if I ran a little fast over this, let me wrap up again what happens here. That's a requirement of bottleneck. xi times ai is at least ei. That replaces the xi times rij is at least ai. Where this is just a normal to the a vector is a normal to the upper boundary of Q. Here again the entitlement. So this means that we have to satisfy this inequality, but I know that this is 1, and I know that this is 1. This means that in the system of inequalities, all of them must hold with equality. In other words, and again, as I said, if this was a little too fast, this is precisely now we have reformulated the problem in the case of a domain with a smooth upper boundary. What we're looking for is a positive vector x, where f of x is 1. This means it lies on the upper boundary of Q, on the smooth upper boundary. And you have this system of equations. ai times xi is ei times the constant. So this vector, where the I coordinate is ai times xi, is proportionate to the vector ei. And A is the normal, so again, x lies on the boundary of Q. It satisfies x is positive and f of x is 1. The normal to the upper boundary of Q at this point x is the vector A. And the condition is exactly what's written here. You multiply A and x coordinate-wise, and you get a vector that's proportionate to E. So the advantage that we've gained here is that now fairness has become a system of equations. Okay, good. And in fact now, so what? AI depends on x. A is the vector. A is the normal vector to the upper bound. It's a good thing to repeat it. A is a normal to the upper boundary of Q at the point x. Okay, what f are we going to choose? That's the most natural choice. You can make many such choices. What about what happens to this function? You remember that this expression had to be non-negative. So when I sum minus the logs, this is a positive function. It vanishes near the origin of the quadrant, and it goes to infinity as I approach the boundary of P. So this is the f that I'm going to work with. Instead, I'm not quite going to work with this. What I'm going to work with is I'm going to, for every positive t, I'm going to consider this domain. X is positive and f of x is less than or equal to t. And I'm going to solve the problem there. And my solution is going to come from a passage to the limit as t goes to infinity. So let's see how this goes. Think of this picture this way. This polytope, or polygon in this case, is P. These are the QTs. And what I'm going to do now, so I'm going to solve this problem using standard stuff from ordinary differential equations for each QT. And I'm going to pass to the limit as t goes to infinity. So on each QT, what I'm going to do is seek. So QT is defined by this, where f is this expression with the logarithms. On each such thing, I'm going to find a point where equality holds and the normal times the x is proportionate to E. That I can do using standard things from differential equations. And then I want to pass to the limit as t goes to infinity. So this picture shows you, first of all, the polytope P, then these different QTs. And now you can start seeing at the origin, it's very easy to solve this for t equals 0. I won't go into the details. And now, as I go up with t, you see I have something like this, which takes me to... So that's the idea of the proof. So what remains to be done? This is at the moment, this is realized by a MATLAB program that does it, but we would like to have a honest polynomial time algorithm that solves the problem that we don't have. I don't think this is very difficult, but we still don't have a very good idea of what the solution set looks like. So one more thing about this not being a linear program. Generically, when you fix the set J, there is a thing. So the solution set is a discrete set of points. You fix a set J, then generically the solution is going to be a single point. And it might be interesting to see whether we can select among them according to other criteria. In particular, can we guarantee a high utilization of the resources? And while keeping things fair, we still don't know about that, and this is where I stop.
This polynomial just go singletons. That's what you said, the last sentence? Generically, J is singleton, right?
No.
Oh, so what
No.
was
No. Fixing, you fix J. As I said before, if you go over all J's, when J is fixed, you're only solving a linear program. For a fixed J, for a fixed set J, you solve this linear program. Generically, its solution is just a single point. Okay, so for each J, you'll get a single solution. This is your solution set. Please. At the moment, I don't have anything in the, I cannot say anything about polytime. I don't think it should be too difficult, but I think we were all exhausted after this project. So.
But why do you believe there is a polynomial algorithm? It could be complex of fixed points.
Why do I believe? I don't know why. Well, I really think that something a little like this game. You deserve a more serious answer. I think that something like this game can be done at least approximately with using some perhaps quadratic programming or things like this. That I think this can be imitated by polynomial time algorithm. But I don't know how to prove it, and if I knew, I promise I would have done it here. So I think it can be done. I don't think it requires some fantastic ideas, but we don't know how to do this. Ever.
So you showed us in the beginning this sort of unfairness of the example you created. It had the property that, you got your sort of share, but, other people didn't seem to want this resource, and they have a really much bigger X than you have.
Right.
So it would certainly be more convincing as a fair thing if everyone using the same J resource, or say that this is a resource that I decide apportion proportional to the everyone's getting his fair share on this resource, so that's why.
But I doubt that this. But I doubt that this can be done.
Good point. That it won't exist. So here is a proposal for something that I don't know if it exists. I like to not name a resource, but name a linear combination of resources. Could say, in your example, could say that, look, the bottleneck is the sum of all the resources. You all got one.
No, but only, no. You cannot have bottleneck. I mean, a combination of resources is going to be bottleneck only if they each individually are a bottleneck.
But I'm declaring the fairness on the sum. In your example, that would create the right thing. Make everyone give you a cert. Said the bottleneck is the total of the three resources, and to divide that fairly, we have to give everyone a cert.
We can discuss it. I'm not sure, but we can discuss. I'm not sure about this definition. No, I mean, this definition is not carved in stone, but I challenge you to find. So I don't want to get into this. And recently there was work also in systems research, looking for other definitions. I don't know of any definition that is better than this one. I agree it's not the most obvious. As I say, it took me sometimes until I got used to it. But now, finally, I've become a believer. So after some time.
One way of viewing this thing is that these are factories that produce some item using raw materials. And therefore, you have this proportional use of raw materials, and all this makes sense. And then the endowments or the entitlements somehow be related to how much funding you have. I wasn't quite clear on the justification
Yeah, in fact, Daniel Lehman suggested to me that he told me I didn't know about this. At least in the Los Angeles area, there is a production of gases that you know, there is a whole market where your factory is buying the permission to generate some pollution permits. There is a, okay, you guys know, I don't. And he said that, for example, this could fit a situation like this. No, you know, I don't know. Is Dror here? I don't know. It's easier for me to stand behind the passage to continuous things. You know, this is where I'm more at home. All I'm saying about the definition that I think it's a reasonably natural definition, which, as I said, it took me some time to get used to it, and I don't know a better one. So if you can come up with a better definition, fine.
This is absolutely beautiful. Now,
Thanks.
my question is, I also agree with your fairness. It's a fair definition of fairness. But would that method of continuous approximations also be applicable, for example, if you have a price for a unit of production by each of these partner or entities, and you want to maximize the total value of
Right.
what they all together produce,
Right.
or would that reduce to a simple linear program?
Yeah. So this is.
If it doesn't, then that method may.
This is something that we really don't know much about, and I think it's still a good subject for investigation. We don't know much about this, but I think this is the approach that is the most promising. I mean, for example, let me just say one quick thing. I know I was a little fast when I spoke about this, but this choice of f that I introduced, that's very arbitrary. Just, you know, I could put in some positive coefficients here, and nothing in the structure of the proof would change. On the other hand, it would lead me to a different optimal solution. So perhaps with a clever choice of this function f, I can achieve additional goals here. I don't know, but this is, you know, I told you what we know. Nothing beyond that.